Hey, welcome back. So before we basically just crushed challenge number 6 over here. We made our array consecutive. We made an efficient, readable, and dare I say elegant algorithm. So now we want to do the same thing with this task number 7 here, almost increasing sequence. The only problem is that this one is a particularly difficult task. It's kind of disproportionately difficult to the ones that come before it. So what I've seen with a lot of people, a lot of new coders, their experience is that they crush the first several of these and then they get to number 7 here, and it just destroys your confidence. So let's attempt this one now. We'll give it a try. We'll see what we can do. Uh, we'll try to get a sense for the algorithm. One thing we noticed in the last video is that you really want to have a good sense of exactly what the problem is asking us to do. We really want to conceive of the problem in the right way. We want to have a good model for how we're going to solve it. So first, let's get a sense of what it's asking us.
Given a sequence of integers as an array, determine whether it is possible to obtain a strictly increasing sequence by removing no more than one element from the array.
Okay, so let's think about what that means. So first of all, a strictly increasing sequence. Basically, the idea is that we want numbers that are going up each time. And the strictly part of that, the strictly increasing, means that even if we had an array that was like 1, 2, 2, 3, that wouldn't be good. Let me provide a visual for that. Here, I'll do it a bit different. 1, 2, 3, 3. So the 1, 2, 3 part of it, that was fine, but the 3, 3, that's no good. It's not increasing there, so that's a problem. If we made it something else, 1, 2, 3, 7, this is fine. It's strictly increasing. There's no problem here. If we do something like this, now it's a problem again. It's not strictly increasing. But in terms of what the problem's actually asking, it's saying, can we get a strictly increasing sequence by removing at most one of the elements here? So basically, the idea is that if we were to cut out the 2 here, the -2, then we would have an increasing sequence, a strictly increasing sequence. So by cutting this out, we'd be fine. So that means this array should pass. This should return true because we can get a strictly increasing sequence by removing one of the elements. Uh, so that's basically what it's asking us to do. Now, in terms of what we're going to use, there are a couple new functions I want to show you for how we're going to do this. But before we do that, let's start by just writing a function to check if something is a strictly increasing sequence. So I'm going to actually make a separate function inside this one. So it's going to be another function. It's going to be called isIncreasing. And it's going to take an array as its argument. And basically, the way it's going to work is it's going to say, well, first of all, it's going to run through the array. So it'll say, we'll do a for here, for loop. For var I is 0, I is less than array.length, I plus plus. So it's basically running through the whole array here. And you remember last time we found that there's actually a much more efficient way of doing this. You know, we could just say like for something like num of array, and that's nice and efficient. We don't need to worry about actually finding the number corresponding to that index. But there's a reason I don't want to do it that way this time. So the reason is actually because I'm not going to start at 0. I'm going to start at 1. So that's part of it. We've got that exception. We're not going to actually start with the first thing. We're not going to start with element 0. So we're going to disregard this element. We just want element 1, element 2, element 3 in this case, or just element 1 and element 2 in this case. So basically the idea is that we're disregarding that first one. The reason for that is we're going to do a conditional here, so we're going to do an if statement, and it's going to say if array at I is less than or equal to array at I minus 1. Okay, so if the current element is less than or equal to the previous element, well, that means it must not be strictly increasing. So if that's the case, I'm just going to say return false. And if it can basically make its way through the entire array without that happening, then that must mean it is strictly increasing, so I'll return true in that case. Now, in case you're wondering why we're starting at 1 and not 0, it's because of this minus 1 here. If we started at 0, then it would be trying to compare the first element to a non-existent element before it, so it would have an error with that. Whereas in this case, it's basically just doing all the comparisons it needs to. It doesn't need to have an extra one. I mean, if you have 4 elements, there are only 3 comparisons we're going to make. So it only needs to go through 3. So that's our function. Right now, it's just being sort of declared as a function, though. We're not actually running this function yet. I mean, we're going to be running the bigger function that it's wrapped in, but we're not actually running this smaller function yet. So we could run it by just doing something like return is increasing sequence. And this will actually probably pass a few of the tests. So if we look at it, it's passing the first one, the third one, the fourth one, like quite a few of these it's passing. And the reason is because some of these are either not going to be possible to turn into increased sequences, and therefore they must not already be in increasing sequence, or I believe there are probably some of them that start out as strictly increasing sequences from the beginning, and therefore will return true, because if you have a strictly increasing sequence, then if you remove an element from it, it's still going to be strictly increasing. So we didn't actually have any in there. Let's make one. So actually, that's perfect. 1, 2, 3. Let's return true for that. In this case, when we run the test, that should check out. We should get true. Yeah, we're getting true because that is strictly increasing. 1, 2, 3 is strictly increasing, whereas something like one of the other tests, like if we look at this 1, 3, 2, 1, that's not strictly increasing, so that's false. So then what about these ones that's getting wrong? Look at this one, 1, 3, 2. Well, it's not strictly increasing. It's not itself going up. But if we were to remove the 3, then it would be strictly increasing. So we should actually be returning true for that one. But how would we know? I mean, the brute force method here would basically be to say, well, if we can only remove one element, let's try removing the first element. And we're just left with 3 and 2 there. So that wouldn't work. That wouldn't be strictly increasing. So instead, let's try removing this middle element here, 1 and 2. Is that strictly increasing? Yeah, it is. And I mean, for what it's worth, we could remove this one as well, and that's still strictly increasing. So there are a few ways we could do it here, but the main thing is that our brute force algorithm here would be one where we actually look at every possible array that would result from removing a single element. So let's give that a try. We might as well get that started, see if we can pull off a brute force algorithm in this case. We are going to have to keep in mind our time complexity. We talked a little bit about that last time, the whole big O business, but we'll get to that. So for now, we've got this function. We're going to keep this function. We'll use that because basically our plan here, and here, maybe we'll start outlining a plan. So we're going to we're basically going to generate all, I guess I'll call them subsequences, but basically what I mean by that is we're going to generate all of the subsequences minus one element, basically. So any subsequence that we can get by removing just one element from the original sequence here, we're going to basically go through all of those. And then for each of them, we're going to check if each of them is increasing. Whoops, I was kind of trying to style it like I had up there. Is increasing. Yeah. We basically want to run this function on each of our subsequences that we're going to get after subtracting that one element. So we need to talk about a few array functions, these guys, the slice and splice, because that's what's going to allow us to actually get that copy of the array without that one element in it. So we'll talk about slice first, and then, well, actually, maybe we should talk about what we're actually going to do in this case. So we'll check if each of them is increasing. If yes, we're just going to return true. And then basically, if not, we'll just continue the loop. If not, continue. And then basically, if we get to the end without finding an increasing one, then we'll return false in that case. So I can actually just change this right off the bat to false, because we know if it gets to this point in the algorithm, we must not have found it, so we'll return false. Okay, so basically this is all the stuff that we want to do. But before we can get to any of that stuff, let's talk about slice and splice. We're going to start with slice. These are really, really similar sounding functions. Like their names are very similar, but in terms of what they do, they're really different. Actually, in some ways, they're opposite. So let's look at an example. So let's just say return sequence dot slice, and we'll say 1, 2. Slice takes, well, it takes a variable number of arguments, but it'll take 2 arguments, maybe fewer than that. So return slice 1, 2. I might even get errors for some of these. So you'll notice it's just the 3 here. When I'm saying slice 1, 2, I'm basically saying I want you to start at index 1. So again, this is 0, this is index 1, this would be 2, this would be 3. I want you to start at 1 and end at 2. So it's basically just getting the 3 in this case. Whereas if I were to say 1, 3, instead of just returning an array containing 3, you'll notice it's in those array brackets here. Instead of just returning the 3, if I were to do it this way, it should return 3 and 2, because it's going to start at index 1 and it's going to end at index 3 and not include index 3. So it does include the first one. It does not include the second one. So keep that in mind. If I run this, I'm expecting to see a 3, 2. There we go. Now, if we look at some of these other ones, this one is also 3, 2, because those happen to be the elements 0 and 1 of that array as well. If we look at this one, we're getting 2, 1, because it's chopping out that part right there. I'm wondering if there are any that are too small, like if there's an array of just two elements. But yeah, maybe we'll try this differently. We'll make this a 5, and we'll see how it runs there. So we're asking for an index that's beyond what this one has. This one doesn't have an index 5. It doesn't even have an index 4. So it's basically giving us as much as it can. It's starting at the 1, and then it's ending, well, at the end of the array. There's another way to do that. Let's say I didn't know where it was going to end, but I just want everything from index 1 onward. Like if I just wanted to drop that first one. So, I could try like doing this sort of thing, just 1 to 500. But that's probably not the best way of putting it, because what if it did have more than 500? I mean, look at our constraints here. These arrays can get big. 10 to the power 5, that's 10,000. No, that's 100,000. That's real big. Anyway, the point is, we don't know if 500 is going to be enough here. So instead, we're actually just going to use one argument. We're going to say slice 1. That's it. And so it's just going to take everything from 1 onward for all of our arrays here. So 3, 2. Next one should be 2, 1, 2. It's just taking, basically, it's removing that first element. That's essentially what's happening here. Okay. So that's slice. Now, we can actually, this might seem a little silly. We don't even need one argument in here. We can just make it dot slice without any arguments whatsoever. If it doesn't get an argument, it's just going to return the whole array. Like nothing different about it. It's just returning the same exact stuff, or at least a copy of the same stuff. And so you might be wondering, why would I ever want to use that? Like that's just the same as return sequence. Why the dot slice there? There actually is a reason for this. We're going to look at a slightly more complicated example for this. We're just going to say something like var a for array, var a is assigned the value of sequence. And now I'm going to say a at 1 is assigned the value of 17. Okay, and so now if I return a, then it should be the same as sequence, except basically the second number we see should be a 17. Second number because, 0 would be the first one. So again, exactly what we were expecting. It's the same as sequence, except instead of this 3 here, we have a 17 because a at 1 is 17. Okay, so that's a. It's a copy of the sequence. We've made a copy of it. We've changed some part of it. We've changed some part of a, so that shouldn't affect sequence. Like if we return sequence, we should expect that to be just the same as it started, like 1, 3, 2, 1. Oh, but wait. We're still getting that 17. Is that a mistake or something like that? I mean, like, that's what A is, but this shouldn't be what sequence is. So this is revealing a behavior that's maybe kind of counterintuitive for a lot of new programmers. This has to do with pointers and addresses, and you can look into that in more detail. But the main thing here is that A and sequence are two different names, two different variables that are pointing to the same array. So there's an array in memory. In this first example, it's 1, 3, 2, 1. Sequence is pointing to that array, and A is also just pointing to that array. So when we make a reference to A, we're making a reference to the same array that sequence is referring to. So if we change A, we're changing sequence. They're both pointing to the same thing. They are both the same array. They're not just two arrays that contain the same elements. They are the same array. It's like having two different names for the same person. So A is almost like, you can think of it as like a nickname for sequence right now. But this is where we can sort of see the difference between just saying A is assigned the value of sequence and saying A is assigned the value of sequence dot slice. Because now when I run this, what we're going to find is that it shouldn't affect sequence because now it's actually making its own copy. So we made a copy of sequence. We're calling it A. We're changing part of that sequence. We're changing one of the elements. But even though we've made that change, it's not affecting sequence. So sequence is still showing me 1, 3, 2, 1. It's still the same sequence that we started with. Whereas if I return A, now I'm getting that 17. So we find now sequence and A are actually different things. They are different arrays that happen to contain the same elements. So anytime you want to make a copy of an array and you don't want it to affect the original array, do this. Do a dot slice. No arguments, nothing in here, unless you want to chop some part of it off. But if you don't, just keep it like this. Okay, so that's slice. You'll notice, the way it's used it's almost a little strange because when we think of slice, like semantically, we think of it as giving us some sort of subset of an array, or a subsequence. But in this case, it's just making a copy. So a lot of the time, for me anyway, when I use slice, a lot of the time it's just because I want to make a new copy of the array that's not going to affect the original one. And if you think about it, that's something we're going to have to do in this algorithm because we're trying to generate all these subsequences. We don't want to keep messing up the original one. We want to keep that one sort of the same. So we're going to use slice for that. And while we have this here, we might as well talk about splice. We understand slice now, so I'll slice it from the list. But we want to look at splice. Splice, it sounds similar, it's quite different. So we're going to look at a few things here. So we'll just keep A the same. And now we'll return A dot splice. And we're going to see how this works a little differently than the previous one. So I'm going to start with 1, 2, just like what we had before. Splice 1, 2. Okay, so now I'm getting 17, 2. Let's even just maybe scratch this line right here just so that we can compare it to the original array. So 1, 2. So this is kind of similar to what we got from slice, actually. It seems really similar, actually, because basically for slice, it would just start from index 1 and then end at index 2. So for slice, when we did 1, 2, we actually just got the 3 here. The reason we're getting the 3 and the 2 is because for splice, it's not the same. We're not saying the start index and the end index. Instead, we're saying this is the index we want to start at, and then this is how big we want the chunk to be, how many things we want to be taking out of it. So in this case, because this is a 2, that means there are going to be 2 things here. So I could start this later. I could say start at index 2 and give me 2 elements, and instead of 3, 2, now we should expect 2, 1. So we'll run the test on that, and we'll get our 2, 1 here. Okay, so splice is a bit different. But maybe it doesn't seem that different, maybe it doesn't seem different enough to sort of justify this this different syntax. So there's kind of a behavior of splice that that I want to reveal. So first of all, let's say var b is assigned the value of a.splice 1, 2, the way we had it before, and we'll say return b. So now returning b, we should get, yeah, the 3, 2. It's just this chunk. It starts at index 1. It contains 2 elements, so it's going to be 3, 2. We got it. It's what we expected. But here's where things get really interesting. So now I want to actually return a. And, well, it doesn't really seem like we've done anything to a, right? We said a is sequence.slice, so it should be the same as this, 1, 3, 2, 1. We're modifying b here, and now we're going to return a. So, I mean, we should expect 1, 3, 2, 1, right? I mean, it should be just the same as what it started with. But this is weird. We're just getting 1, 1 instead. We're not getting the 3 and the 2. It's not a coincidence that the 3, 2 is exactly what we cut out with our splice. So basically the way splice works is we say it's destructive. It actually does damage the thing that we're modifying. When I do a slice of sequence, I'm not affecting sequence. Sequence stays the same. When I do a splice on it, though, it does affect it. So splicing A will change A. We'll actually take that 3, 2 and remove it from the array. So it's just the 1, 1 that's left now. Let's modify it slightly. Let's say splice 1, 1. So now it should just be taking out 3, which means that A should be 1, 2, 1, and B should just be an array containing 3. So we'll look at A first, 1, 2, 1, as we expected, and then B should just be that 3 in singleton 3. Yeah, there we go. So basically an array containing just the 3. Okay, so that's the difference between slice and splice. Splice, you may have guessed it, it's what we're going to be using to cut out each of our elements. It's what we're going to use to, cut out the 3 in this case, or we'll use it to cut out the 1s, cut out the 2. Like we'll go through each of these until we find one that's strictly increasing. Or maybe we won't find one that's strictly increasing, in which case we'll go through all of them and then we'll return false at the end. Alright, so that's slice and splice. Again, very similar sounding, but pretty different in terms of their action. Okay, is there anything left to say about this? Oh, well, I guess one thing. For splice, we can actually give it a third argument. I'm pretty sure it's the third argument where it would sort of replace almost the thing that we splice. So like we'll take out, in this case, just the 3, and we'll replace it with, I don't know, 5. I'm pretty sure that's what the third argument does. Yeah, so 5 in there. Or I guess the word dog. They don't all have to be the same type. I mean, there's not really a reason why we want to do this, but that doesn't stop us from doing it. Anyway, again, if we wanted to take out a chunk of size 2, it's replacing the 3 and the 2 with the word dog in this case. All right, I'm going to stop that. So what we want to do in this challenge is basically we want to cut out one thing at a time. And which thing is it? Which index do we want to start at? Well, that's the thing that's going to change. So basically, with these two functions in mind, we're gonna do a little loop. So we'll say for var I assign the value 0, I is less than sequence dot length I plus plus. And then from here, and again, maybe we'll clean up this for loop later, but for now we're just going to keep it like this. So we'll say, first of all, var copy. We'll call it copy, and just, again, to make it clear to the reader what this thing is actually doing. Like, we could call it A, we could call it B, we could call it whatever we want, but in general, you want to use a name that's going to make sense to the reader. Again, the reader might be you in the future, so make it something that's going to make sense to you, something that sort of speaks for itself in terms of what it's doing. So this is a copy of our sequence. We could even call it sequence copy or something like that, but I mean, we don't want to get to a point where our variable names are so long that it's making it harder for us to read and understand the code. So that'd be counterproductive. So basically, we'll leave it like this, and we'll say copy is sequence.slice. And then from there, we want to say maybe var subsequence. Call it subsequence. And it's going to be, well, actually, maybe we should just call it subsequence instead of copy, because we are going to be modifying it after all. So here, var subsequence is that. And then we'll say subsequence. Subsequence dot splice I1. So basically the idea is that we're just taking out that first element, or whatever element, we're going to run through. It's going to go from 0 all the way to the end of the array. So first we'll cut out the 0th element, then we'll cut out the first element, the second element, third element, and basically eventually we'll do some stuff. We'll do some of this business, but for now, I just want to cut this out, and I'm going to do a console log just so we can see what each of these subsequences are looking like. This is going to return false because that's what we have down here, but we should be able to see the subsequences. So looking at this first one, we could cut out the 1, which would leave 3, 2. We could cut out the 3, which would leave 1, 2, or we could cut out the 2, which would leave 1, 3. And we're looking at this first one up here as well. Cut out the 1, we get 3, 2, 1. Cut out the 3, we get 1, 2, 1. Cut out the 2, we get 1, 3, 1. Cut out the 1, we get 1, 3, 2. So this is doing what we want it to do. This is generating all the subsequences minus 1 element. So I'll just pop it in right there because that's, hey, it's doing what we want it to do. Okay, there we go. So this is, hey, so far so good, right? Now we want to check if this subsequence is increasing. So we're not doing too bad. We'll say, well, let me just delete this line. We'll start fresh here. So we'll say if is increasing subsequence, then we're going to return true because that means we found it. We found one where it worked. So check if each of them, maybe I'll just say check if the subsequence is increasing. And if it is, we're going to return true. If not, we're going to continue. I think that at this point is kind of self-explanatory. And if we get to the end without finding an increasing one, we're going to return false. Oh, and I'll just delete splice because we talked about it. Okay, so let's run the tests on that guy. We'll see how it goes. Look at that. We passed all the sample tests. Okay, so this is great then. We have an algorithm. It's working the way we want it to. It makes a lot of sense, hopefully. I guess that's it. So, I mean, our algorithm, it's looking pretty nice, I think. It's pretty clear to read. We've got nice comments in here, which are always a nice thing to provide for your reader. And so at this point, we're ready to fire that off and just get it submitted. So here we go. We'll submit that. And, oh, look at that. So we passed 29 out of 30 tests. The problem is that on one of the hidden tests, notice we're passing all the visible ones, on one of the hidden tests, we're getting a time limit exceeded. So, okay, this is a good teachable moment here for the console. Notice it's not saying you got the wrong value. It's not saying you got everything right except you got this last one wrong. It's saying you exceeded the time limit on the last one. That's the problem. It took too long. If we had an infinite amount of time, if it was up to us to just sort of wait for this thing and let it execute, we'd be fine. But we have a time limit here. We only have 4 seconds. It's got to get done in 4 seconds. It's got to go through all 30 tests in 4 seconds. If it doesn't, that means we have a problem with our time complexity. We have too long of a computation time here. Okay, so we'll talk about this now. Basically, the idea is that if we're looking at this, it's going through it's going through the sequence, basically, the length of the sequence, because it's generating subsequences, all the possible subsequences consisting of one missing element. Okay, so basically, if the sequence has, let's say, 10 elements, then this loop is going to execute 10 times. The problem is its calling is increasing with subsequence, and is increasing also has a for loop that's going through that whole array. So again, if our array has length 10, then each subsequence will have length 9. This is going to execute 10 times, and within each of those, this loop is going to execute 9 times. So even though the length of our array was 10, now this is executing 90 times, which is a lot more. It's a lot worse. If we look at our constraints here, here's where we find the real problem. The length of our array sequence can be as much as 100,000. We can have 100,000 elements in the array. If that's 100,000, it's got to do this loop 100,000 times, and every time it does that loop, it's got to go through this loop 100,000 times. So we're getting into a pretty damn big number there. I mean, that would be like 10 to the power of 10. So what's that, 10 billion? It's got to do 10 billion iterations. That's too damn many. That's going to time out. Well, it did time out. We can see that right here. So that's really important. This is good information, because if this was just saying that it was wrong, test 30 was wrong, then that means there's something wrong with the way our algorithm's thinking. The fact that it's saying the time limit exceeded means it's thinking just fine, like it's doing the right thing, it's coming up with the right answers, but it's just taking too long to do it. And it makes sense. We can have huge arrays here, and really, to be honest, this is the reason that this one task stands out as being particularly challenging amongst the rest of them. If it weren't for these constraints, if we didn't have a 100,000 length array here, it wouldn't be a problem. We wouldn't have an issue with this. So, I mean, or at least what I should say is this algorithm would work. This algorithm would not be a problem. Right now, it is a problem. We'd say this is something like a big O of n squared, where n is the length of the array, because, like we saw, it's a for loop, essentially a for loop within a for loop. It's a nested for loop, and each one of those loops is going all the way through the array. So we've got basically the length of the array squared. That's the number of iterations. That's the number of operations that are going to happen here. Too many. So we need to rethink our algorithm. And we saw a bit of this last time. Basically, the idea is that we need to think about how to conceptualize this problem, how to look at this problem in such a way that that allows us to come up with an algorithm that's well, faster. That's the main thing. Okay, so I'm going to look at my whiteboard here. It's got stuff on it from before, so we'll clear this. I think we can just sort of cut everything out. And there we go. Okay, so basically what we're looking at here is, we'll look at this in the form of a graph, okay, or a scatter plot kind of thing. So we've got some numbers, and maybe maybe they're strictly increasing. So this would be fine. This would pass. This wouldn't be an issue. This we'd return true for this one. And you know, maybe it's like 2, 5, 7, 9, 13, 17, something like that. You know, like it's a strictly increasing sequence. Okay, so this would pass, but this isn't very interesting. You know, this is pretty plain. It's not a very interesting example. What's a more interesting example of something that would pass would be, well, something like this. So now we have this strictly increasing sequence plus this additional element which we'll say without loss in generality, it's right here. You know, maybe it's over here, maybe it's over here. It doesn't really matter. It's wherever you want it to be. The point is we have this element now. And this would pass. Now, if we had another element that was out of sequence, like if we put this one down here, for example, now this wouldn't pass. This has too many elements that we'd have to remove in order to actually get that strictly increasing sequence. So that's no good. We can't have that. But we'll just have this one extra element, we'll say. Okay, so the way we're going to check for this is we're going to point something out. So first of all, I guess there's no way I can copy this, so I'll just run through these one at a time. We'll switch colors. I want to point something out about our diagram here and what we're actually looking at, because this is a very good general example of the type of sequence that's going to pass, that, you know, where we should return true for something like this. In fact, what did we say this was? So maybe it's okay, 2, 5. We'll say 2, 5, 7, 13. Okay, let me get this down. So 2, 5, 7, 13, and then 9, 12, 17. Something like that. And for this one, this should return true. It should work. So let's just verify that that's returning true, because it should at some point remove the 13. There we go. Yeah, so it would remove the 13. It's basically going to iterate up to that point. It's going to try removing the 2. That's not going to work. It's going to try removing the 5. That's not going to work. It'll try removing the 7. That won't work. It'll try removing the 13, and it'll say, oh, okay, that works. So we'll return true. And remember from last time, as soon as it returns true, it's not continuing. It's not going to execute the rest of the functions. So that means it's not going to return false. And also it means it's not going to continue looping through this function. It's just going to stop as soon as it returns true. That's it. Okay, so at this point, let's go back here. We know that this should return true, but let's take a close look at it. I mean, this is basically the way something looks, the way one of these sequences is going to look if it's going to return true. And we can look at it as being sort of this one increasing sequence with this outlier over here. But there's another way we can think about it, and this is maybe going to be a helpful way to think about it. So we can say, well, it's a strictly increasing sequence, and then it's another strictly increasing sequence. Is that going to be a helpful way of thinking about it? Well, I would argue, yes, it is, because it means the way we can check for this is we can just say, while this is increasing, you know, until this stops increasing, keep going, you know, iterate. Have an iterator that starts all the way to the left and basically just kind of closes in as far as it can. Now, it'll get to this point, but then it says, oh, well, no, this is a drop off here, so we're not going to include that next point. It's just this. This is our strictly increasing subsequence here. And then we can also look at it from the right and go in the other direction and say, well, as long as this is decreasing, then we're going to keep going. And again, it would stop here because it'd say, all right, well, this goes down, that goes down, that goes up, so we're not going to include that one. So this is our decreasing sequence over here. Okay, so basically we have these two iterators, one that goes from the left, one that goes from the right, and my claim is that if they meet here, then that means it'll pass. It'll return true. It should return true if they meet in the middle. And just to sort of show you a counter example, I guess, we could draw another one of these over here, and let's just look at some other kind of random sequence. So maybe it goes up, down, up again, down again, down again, and then up. Okay, so again, that's kind of a random sequence. It's going to go from the left, it's going to go up until it's no longer increasing, so it's going to cover that. And then from the right, it's going to keep going until it's no longer decreasing, so it'll stop here. And the issue here is they're not meeting in the middle. My left iterator is not making it to my right iterator. So in this case, I'm going to return false because they don't meet up. Okay, that's broken heart. Anyway, all right, so that'll return false. This will return true. And so that's an easier way to check. I mean, that's a much more efficient way of checking because it just means we'll travel from the left and then we'll travel from the right. We're not looking at chopping up the array in a bunch of different ways. We're not looking at all the different subsequences that are possible. We're basically just doing an iterator from the left, an iterator from the right. We're actually just traversing the whole array one time. That's it. We don't have to go any further than that. Okay, so let's look at a few other cases before we go any further. Just to make sure this is okay. Just to make sure this will work consistently. So I want to sort of redraw what we have here already. So we had 3 of these going up, and then another 3 going up after that. And then we had this extra one. Now over here it was above. It was too high. But what are the other possibilities? Well, I mean, if it's somewhere in here, that's really not that interesting because that means it was strictly increasing to begin with. So we're not going to do it like that. If it was down here, well, that's a bit different now. That's something worth considering. So let's take a look at this. Basically now our left iterator is going to go only this far because it would be a drop to get to that yellow point. Whereas our right iterator will include it because it wants to be decreasing as it goes from the right. So even though in this case it was above and in this case it was below, our left iterator is still meeting up with our right iterator, which means that we should definitely return true for this one. And we should, because if we were to just cut this guy out, it would be a strictly increasing sequence. Okay, so that's basically how we're going to check for it. There's just one maybe extra element that we'll need to talk about in here, but fundamentally, this is how we're going to do it. We're going to have 2 iterators. We're going to have a left one that starts all the way to the left and will travel right as long as the values are increasing. And then we'll have a right iterator that's going to start at the right end and then travel backwards. It's going to go back as far as it can until it's no longer decreasing. And then after that, once that's fully executed, we'll sort of take a look at some of the possible outcomes here, because there maybe is sort of an exception that we're not looking at yet, but we'll deal with that when the time comes. For now, let's go back over here. This was our beautiful algorithm that we had written. It was, I mean, we're very proud of this. It was good for 29 out of 30 tests. I mean, it really served us well, but not well enough because it didn't pass that last one. So I'm going to comment the whole thing out, and we're just going to try to start fresh over here. So basically, like I said, we're going to have a left iterator, and it's going to start all the way to the left. And we're going to have a right iterator, and it's going to start all the way to the right. So it's going to be sequence.length -1. And the reason I'm saying -1 is because we want it to start on that final element. So basically the idea is that in this case the length is 4, but this element would be index 3. So we'll put it right there. Okay, so at this point, let's start moving through these. So I'm gonna say, how should I do this? Okay, I'm going to say while left is less than sequence.length. Or I guess I could say while left is less than right. Maybe we'll do it that way. While left is less than right. I mean, there's not a huge difference there. The main thing is just that this way I don't need to check the length of the sequence again. We already know what it is, so we don't need to call the length function again. That's not the sort of thing that's going to make a huge difference. You know, like that's not the sort of thing that would make the difference between passing and failing that 30th test. But it's worth considering. I mean, keep these things in mind. Okay, so going back to this, while left is less than right, well, what do we want to be doing here? Basically, the idea is we want to say, well, if the sequence at left plus 1 is less than or equal to the sequence at left, then that means we're getting a next element that's less than or equal to the previous one. So if we're looking at this, moving through from the left, is 3 less than or equal to 1? No, it's not. Is 2 less than or equal to 3? Actually, yeah, it is. So we actually want to stop there. We just want to include the 1 and the 3 in this case. So the way we'll do that, is we'll break. The way break works is it just breaks out of a loop. It basically means we're going to stop iterating. We're going to stop doing this loop once we see break. Now, there's a similar keyword that's called continue, and it basically means we'll stop this iteration and we'll just move on to the next one. Forget anything that happens below this, we'll just move on to the next one. In this case, we don't want to move on to the next one. We actually want to exit the loop at this point. The thing is, if I were to execute this right now, this would be an infinite loop because left isn't moving anywhere. So I actually need to move left along. I'll do left plus plus. And, there are different ways we could do this. We could put the plus plus up in here if we wanted to be more efficient about it, if we want to do some fancy stuff. But for now, we'll just do this. We'll do left plus plus. Now, just to see if this is working, let's just return left. We'll see how far it's getting, if it's doing the thing that we want it to be doing. Okay, so left goes as far as this in this case. 1 and 3, those are both increasing, so left goes as far as the 3. In this case, again, it goes as far as the 3. In this case, it goes as far as the 2 because the next one is a decrease. For this one, 1, 4, and 10, that's all increasing. It's not until it gets to the 4 that it has to decrease, so it'll get all the way to the element with an index of 2. Okay, so left is, yeah, I think it's working the way we want it to. One thing we need to consider here is if we get to a point where the left actually becomes equal to the right. Like what if we went through this whole thing and it was strictly increasing the whole time? So in this case, 2. So I'm going to say before we go any further, if left is equal to right, if they're now the same value, then we want to return true because that means we had a strictly increasing sequence to begin with. So let's run that. We'll see if it works the way we want it to. Yeah, both of these were strictly increasing sequences from the beginning. Or sorry, this one was a strictly increasing sequence from the beginning, so we're getting a true. Now, this one happened to be true as well, but just because any non-zero number is going to be considered true. So, this could be 3, it could be 5, it could be whatever, and it would still be typecast to a Boolean as true. So that's more just a coincidence than anything that we're getting the check mark on that one. Okay, so we've done part of what we were looking for. We've iterated from the left. That part is done. Now we need to iterate from the right and compare the two, see if they work. So let's get a right iterator. That's after this, because we don't need to bother with the right iterator if it turns out that the left makes it the whole way through. So that part is fine. We won't worry about it. Now we'll say while right is greater than or equal to 0, And we'll basically do the opposite thing. So if the sequence at right minus 1 is greater than or equal to sequence at right, then we're going to break. We want to get out of the loop. And of course, we need to de-increment right in this case. Okay, so now let's see. Is right working? Is it working the way we want it to? So, oh yeah, that one returned true because of this line over here, so that's not actually going to be right. In this case, right is 4. Now if you remember when we were just looking at the previous one, when it was returning left, left was 3, so it's making it all the way up to the 13 here. 4 would be the 9, which means right is doing exactly what we want it to. It's going starting at the right, and it's de-incrementing itself down until it gets to a point where it wouldn't be decreasing if it were to go further to the left. Okay, so right is doing what we wanted to do. Left is doing what we wanted to do. The question is, are they meeting up where we want them to meet? So when we looked at that previous one, which it was this example that we're modeling, we found that left was 3. This is element with index 3. This one would have index 4. So basically, if left is equal to right minus 1, or if left plus 1 is equal to right, under either of those circumstances, it should be true, right? So we'll say return. Well, okay, there are a few ways we could do this. We could do something like if left plus 1 equals right, return true. But that's kind of a silly way of doing it, because that basically just means if this is true, return true. Like this is already a Boolean, you know, this is going to be a true or false value. That's why we can use it in a conditional statement like the if. So what we could just do is we could say return this thing. I mean, this is a Boolean, so we can just return that. Return left plus 1 equals right. Done. I mean, that's really what we're trying to check. So if this is true, it's just going to return true. It's what we wanted it to do. Okay, so it's returning true. This one is returning true as well. So that's great. I mean, it looks like it's working. You know, they met up. They're going to live happily ever after. It's a strictly increasing sequence if we delete this one here. Okay, so that's great. I mean, this should be working now, right? But what's this? We have a problem with our test. Is that the only one? No, there are a couple of others. So we'll use this as an example. It's 1, 2, 1, 2. Okay, let's use the space over here on the right for that example. And I guess I cut this kind of tight. There we go. Oh, and we don't know about that yet, so we'll erase it for now. All right, so 1, 2, 1, 2. So basically that would look like 1, 2, 1, 2. All right. Well, does it have the property we're looking for? So if we increase from the left, we'll go as far as element 1. If we decrease from the right, we'll go down to element 2. So that's 1 right there, that's 2 right there. Well, that seems to have the property we're looking for. I mean, the left here is meeting the right over here. So why is it not working? Why is it that we're not getting the right value here? Well, we're saying, yeah, it should work, but they're saying, no, it shouldn't work. Let's think about it. I mean, should it work? Can we remove an element here that would make this a strictly increasing sequence? If we remove the first one, we get 2, 1, 2. That's not increasing. If we remove this one, we get 1, 1, 2. Well, that's not strictly increasing because 1 is not greater than 1. Otherwise, in this case, we get 1, 2, 2. Again, same reason, not strictly increasing. 1, 2, 1. Well, that's not even increasing at all. So we really should be getting false. So we need to think a little deeper about this. We need to think about our other restrictions on this thing. So basically, the idea is that the reason this one didn't work is, well, let's say this was the outlier. It's not really so much an outlier because what's left over is not strictly increasing. Again, maybe this one's the outlier, but again, it wouldn't be strictly increasing without that. So what we need to make sure of is we sort of need to compare the following things. Let me just clean this up a little bit first, and then I want to point something out here. So basically, let's get that yellow dot back in business. Oh, I'm on eraser. Sorry about that. Okay, there it is. So basically, here, this is what we need to check. We know this is strictly increasing. We know this is strictly increasing. But if we were to remove this, there's one more thing we need to check. We need to compare this thing here to this thing here. We basically need to make sure that this would be increasing when it goes to the next element. So what is this here? I mean, in this case, this is left minus 1, and this is just right. Okay, so I'll use an L for left, L minus 1, and an R for right. So this is just R. Okay, so I basically need to check if sequence at R is greater than, strictly greater than, sequence at left minus 1. Okay, so we've got a Boolean in here. We're going to just put in another Boolean. We're going to say and sequence at left minus 1 is less than sequence at right. Okay, and that should be enough, right? Let's see. Okay, so we're still having an issue. Did we pass? Yeah, we are now passing the one that that was giving us a problem before, but now we're still having a problem with this one. Okay, and this is kind of an interesting situation. I mean, the reason we're having an issue with this one, it looks like left in this case is 0. So left minus 1 would be like -1. There isn't going to be a sequence at left minus 1. So we need to consider that. Okay, so this is going to be a little more complicated. It's not just going to be this. We also need to consider or left equals 0. Maybe left is all the way at the left. Maybe it is 0. Maybe that outlier was the very first element. Okay, so if that's the case, well, is that going to work? You know, if left is equal to 0. Well, notice I put it in these parentheses here. So basically, the idea is that either of these things can be true. This or the second thing. So the first thing or the second thing. That's the double pipe here for the or. But we're only going to get to this if it's already past this part here. This has to be true, because if this was false, the whole thing's going to be false. It doesn't matter what the second thing is saying. So that's actually another good thing to know about JavaScript. When you're dealing with these logical operators like ands and ors, if this is false, you know, a false and anything is still going to be false. False and true is still going to be false. So if this thing is false, we're never going to make it to this second part here. So that's kind of an interesting point. That means if we do get to this point, that means it must have passed this. So in this case, we're saying left plus 1 is equal to right. Left is 0, right is 1. So it does make it past this part. It checks this part. It's going to fail this, but that's okay, because with an or, even if the first part is false, false or true, well, that's true. So we still need to check this one to know if it's true or false. We don't know immediately. I mean, if this one ended up being true, we don't need to check the second part because we know the whole thing's going to be true. Anyway, the point is, it'll get to this point, left is 0. Well, yeah, it's saying left is 0, and by virtue of the fact that left plus 1 is equal to right, it must mean that right is 1 also. So we don't need to get too specific. You know, we don't need to say left equals 0 and right equals 0. So okay, let's give this one a test. We'll see if that's working. So again, we made it past the one that was giving us a problem last time, but we're still not passing all the sample tests. There are still 2 that aren't working. Let's take a look at this one. 1, 2, 3, 4, 3, 6. Why is this one not working? It looks like the 3 is the outlier here. So let's take a look at this one. 1, 2, 3, 4, 3, 6. I guess I'll just clear this area again. And you know what? Maybe I'll just redraw it. That's probably makes most sense at this point. 1, 2, 3, 4, 3, 6. Okay, coming right up. So 1, 2, 3, 4, 3, 6. Okay, so for this one, basically, that one's the outlier. That's the one that if we were to remove it, we'd get the strictly increasing sequence. So we'll just sort of mark that one for now. From the left, it's going to go up all the way up to this point. So that's index 3. And on the right, it's going to go down over here. And that's going to be index 4. Okay. But this is interesting because now let's take a look at what we were saying over here. In this case, we're saying left minus 1 has to be less than right. But that's because the left half here included the outlier in that case. Now the outlier is on the right part of it. So it's actually not this one and this one that we want to be comparing. Which makes sense because those two are equal. It's not going to pass. In this case, it's this one and this one we want to be comparing. So this one is the left element, and this is right plus 1. Okay, so basically it might not be that sequence at left minus 1 is less than sequence at right. It might also be that sequence at left is less than sequence at right plus 1. So let's try that. Okay, or sequence at left is less than sequence at right plus 1. Okay. And do we still have that? No, okay. There's nothing else after that. So we'll try that, and we'll see if there's any tests we're not making it through. Okay, we have just one test remaining. This is pretty good. We're almost there. What's happening in this test? Well, basically, it's increasing, increasing, increasing. Okay, so this is a bit like the opposite of the case we saw where we had to build in this part here. Because now, instead of our outlier being all the way to the left, now our outlier is all the way to the right. If we kill the 3 here, everything will be fine. So the problem with this one is basically we're saying, well, the 3, if you think about the index, 0, 1, 2, 3, 4. Okay, so the index is 4 here. That means right, the value of right here would be 4. When we do right plus 1, we'll get 5. Well, there's no index 5, so we're going to have a problem with that one. So again, we need to build in, or right is assigned, or sorry, right is equal to sequence.length minus 1. So in this case, since right was 4, it was the last index in the sequence, that was, again, an outlier, an edge case we were considering. And again, we got to keep in mind, we're not just saying that right is sequence.length. We're not just saying that right is 4 in this case, because we already know that left plus 1 is the same as right. So that means not just that right would be 4, it also means that left would be 3. So at this point, let's give this a run. And hopefully it's going to pass all the visible tests. Okay, it's passing all the visible tests. So our algorithm is working. It seems like it's covering all the edge cases here. It looks a little messy though, so maybe I'll just pop in a few enters here. So enter for, whoops, I'll keep that on the previous line. For each of these things that it's doing. So for every or for every and, I sort of want to put enter there. Okay, so, and I've got my semicolon at the end. So that's, I think, looking a little better. Still works like that. You can throw in an enter if you want to make your code look a little more readable. It's probably good practice. I mean, we don't really want to have those lines that just go on forever and ever. I think the rule a lot of programmers use is 80 characters. Basically, don't make your line go more than 80 characters. So I think we're good. I don't really want to have all this stuff on my submission. So we'll look back on this. Fond memories all around. I mean, it was such an exciting algorithm at the time, but really, I think we've got a better one here. I'm actually more excited about this one up here. So let's just cut away some of the space here. We'll make sure it's still running just fine. Okay, it's passing all the tests, so I want to give this a submit. I didn't mention this in the last one. You can do Control Enter as a keyboard shortcut or Command Enter. So I'm going to do that. Oops, I guess my focus needs to be over here. So Control Enter. We're going to see if it passed all the tests or if it's going to time out like it did on the last one. But if you think about it, this one really shouldn't time out. And there we go. It's correct. What I'm saying is it shouldn't time out because this one is really a lot more efficient than the last one because we're only going through the array once. It's not that we're going through the array and doing something with every single element. It's not like we have to look at this one and do a whole for loop on all of them, and look at this one and do a whole for. It's nothing like that. We're just going through the array, half of it from the left, half of it from the right. Maybe not half and half, but basically part of it from the left, part of it from the right. But we are just going through the array one time. That's it. So this would be more of a big O of n. This is happening in linear time and not quadratic time. That might not seem like that big of a difference, n versus n squared. But again, consider these limitations. So it's the difference between 100,000 versus 10 billion. I mean, 10 to the power 5 versus 10 to the power 10. It makes a huge difference at the extremes. This is a really good example of this whole time complexity thing, the computation time thing. In the last one, we found that the limitations weren't really that significant. Like there wasn't really anything that they could have thrown at us in the last example that would have made our algorithm time out, regardless of how inefficient our algorithm is. Whereas in this case, we found that efficiency really mattered. The difference between big O of n versus big O of n squared was the difference between passing all the tests and not passing that last test. So I mean, we basically wouldn't be able to move on if we didn't make our algorithm as efficient as possible here. So again, just keep in mind a really important part of programming, regardless of whether you're doing JavaScript or whatever language you're using, a really important part is this, getting down to the pencil and paper, or whiteboard and mouse in this case, conceiving of the problem, thinking about the problem. We want to conceptualize it in such a way that's going to make efficient sense for us. And as we saw, sometimes that's actually going to make the difference. So we can see why that was such a tough task. We can see why the number of solutions for this task is, I think, about half the number of solutions for the previous one before it. I mean, it's a big drop off because it's this. That's really what does it. If we didn't have that limitation, well, we would have been done a really long time ago. So because of this, we need to find a workaround. But look, I mean, that's what real life is like. You want to be making an app of JavaScript. Its natural habitat is on the internet. JavaScript is the language of making websites that do things, and so computation time makes a huge difference there. I mean, that could be the difference between someone willing to sit around and wait for your page to load versus that person thinking, this is taking forever, forget it, we'll get the competitor's product. So these things make a difference. It's important to consider computation time. It's important to consider having a nice efficient algorithm. And again, just like in the last one, I mean, this algorithm it's nice to look at. It's very clear to the reader what this thing is doing. We could probably, if we wanted to make it more clear, we could maybe call this left index and right index. But again, we don't want to be too verbose. We're really referring to the left and right a lot of times throughout this whole algorithm. I know some coders would just call them L and R. That's probably fine too. I mean, it's up to you. Whatever you think is going to be most clear to the reader, whatever you think is going to be worth it. Like it's you who's going to have to keep typing these out a bunch of times. So you've got some decisions to make there. Anyway, that's going to be it for this one. I'm glad we made it through that very challenging task. I would definitely encourage you to keep practicing a lot of these concepts here. I mean, really, at this point, if you can make it through task 7, you probably should be able to make it all the way to task 33 without too much difficulty. in between. 33 is going to be the next one. That's really going to take some heavy thinking. So that's it for now. Thanks for watching, and I'll see you again soon. Bye.